Welcome to Chem in 5. Today, we'll explore hyperconjugation, an essential organic chemistry concept that explains molecule and carbocation stability. So, what is hyperconjugation? Simply put, it's the delocalization of electrons from a sigma bond, often C, H, or C, C, into an adjacent empty or partially filled orbital. This process stabilizes molecules without creating new bonds. Imagine a positively charged carbon, a carbocation, sitting next to a C, H, bond. The electrons in that C, H, bond spread into the empty orbital of the carbocation, reducing that pesky positive charge density. The more neighboring C, H, or C, C bonds there are, the more stable our carbocation becomes. Let's look at some examples. Tertiary carbocations, like tert-butyl, are the champs. 3 neighboring methyl groups donate electrons. Then there's the secondary carbocation, like isopropyl, quite stable but not quite the king. And primary carbocations, like ethyl? They're the underdogs, least stable and always needing help. Hyperconjugation doesn't stop with carbocations. It also explains alkene stability. For instance, 2-methyl-2-butene is more stable than 2-butene or 1-butene, thanks to the electrons from nearby C, H, bonds. Now, why does hyperconjugation matter? It shapes carbocation stability, crucial in many reaction mechanisms like electrophilic addition. It also affects alkene stability, as more substituted alkenes are typically more stable due to hyperconjugation. Lastly, it helps chemists predict which molecules are more reactive or stable in reactions. To wrap it all up, hyperconjugation involves electron delocalization from sigma bonds to adjacent orbitals. It stabilizes carbocations, influences alkene stability, and helps us understand reactivity trends in organic chemistry. If you found this helpful, go ahead and give us a like, subscribe to Chem in 5, and drop your questions in the comments.